الأهلية عمان University in Biomedical Engineering Department. This presentation is to introduce my paper entitled Time and Wavelength Diversity Schemes for Transdermal Optical Wireless Link. First, I will talk about the transdermal optical communication systems, which gained a significant attention in recent years, where the skin is the transmission medium and many conditions will affect the link performance, resulting from skin thickness and pointing error, which represent the misalignment between the transmitter and receiver. This study examined the transdermal optical wireless system by analyzing the outage probability as one of the important metrics used to evaluate such systems, where both skin-induced attenuation and pointing error are included. Closed form expressions were derived under various skin conditions and different pointing error levels. Finally, simulation model using Monte Carlo simulation using MATLAB was used to validate our suggestions, where the simulation result showed a good agreement with the numerical result, which showed the effectiveness of using time and wavelength diversity techniques to enhance the performance of a transdermal optical wireless system. Okay. Recently, wireless medical applications have been the focus of many research, in particular active medical implants, which is an electronic device used to control biosignal to the heart, spine, and brain, or control medical devices like medication dispensers. So, reliable high-speed communication link between a transmitter located inside the human body and a receiver located outside body is required. However, current radio frequency technology not accommodate high data rate required to maintain channel reliability. So, optical wireless communications have been recognized as viable alternative to RF technology because of its superiority in terms of bandwidth, data rate, and interference immunity. Many studies discuss the efficiency and reliability of a transdermal optical wireless system, and many studies discuss the effect of skin thickness and pointing error in a transdermal optical link in terms of data rate and transmitted power. And many studies discuss the different diversity techniques used to improve the performance of a transdermal optical wireless link. Here are some related works with comparison to this study listed in this table. As we see, in 2010, the author represented a lab test bed to measure the performance of a communication system based on wavelength diversity as a function of turbulence amplitude. And in 2012, the authors, considering the use of wavelength and time diversity in wireless optical communication system that operate under weak to strong atmospheric turbulence conditions, modeled by gamma-gamma distribution, and derived the closed form mathematical expression for estimating the system achievable outage probability and average bit error rate. In 2013, the authors investigated a time diversity scheme for a free space optical channel under a strong turbulence condition modeled with an exponential distribution and extracted the closed form mathematical expression for estimation the outage probability, the average bit error rate, and maximum effective bit rate. In 2016, the authors presented a performance study and derived a closed mathematical expression for estimation the probability of fade for on-off free space optical free space communication system, taking into account the pointing error. And in 2018, the authors obtained a closed form expression for the outage probability of the optical wireless transdermal link, which take into account the channel particulars and the transmitter-receiver misalignment, the characteristic of the optical unit, as well as the physical constraints of the embodied device. And in 2019, the authors derived novel closed-form mathematical expression for the outage probability of the total transdermal optical wireless that employs different diversity configurations, either in a space-time wavelength under the effect of non-zero Forsyth pointing error. This study derived the closed-form expression for estimating the outage probability for a transdermal optical system using wavelength and time diversity techniques for the case of selection combining at the receiver under the effect of zero pointing error. Now I will discuss the methodology used. This figure represents the proposed system model where the out-of-body unit consists of data capturing unit that converts external stimulation into electrical signal followed by digital signal processing unit that digitizes and compresses the data into a well-formed modulated signal. Then this signal is transmitted by transmitter to receiver. The received signal is processed via the digital signal processing, then forwarded to stimulation unit to generate the appropriate stimulation. We assume that we have L number of a transmitter and M number of receivers. In time diversity approach, M identical copy of the signal are sent by a transmitter at M distinct time. The copy of energy signal that is received by the receiver is stored in receiver memory. Where in wavelength diversity, the system consists of composite transmitters that broadcast a signal at many operational wavelengths at the same time to multiple receivers. Each of them is tuned to pick up the signal single wavelength. The laser beam travels through the skin, which acts as an additive white Gaussian noise channel, memoryless, static, ergodic, independent, and identical distributed fast-fading channel, which with intensive modulation, direct detection on-off keying. Also assume the channel state information is shared between the transmitter and receiver. As mentioned previously, a transdermal optical link can be modeled as a communication system with single transmitter and arbitrary number of receivers, M in this case. And we use the assumption to simulate the time diversity feature of the transdermal optical wireless link, which involves sending out M copies of each part of the signal. The statistical channel model is presented by this equation, where N is the zero mean Gaussian process, and the nu is the photo diode efficiency, and X represents the on-off keying data information signal. H is the skin channel state, which consists of two parts, HL and HP. HL, which is deterministic channel coefficient resulting from propagation loss skin attenuation, while the second term, HP, is a stochastic process due to misaligned fading. Okay, the outage probability, which assess how reliable that transdermal optical link, and which is the probability that the instantaneous sum of signal to noise ratio gamma drops below a given threshold value, can be expressed threshold value. So considering that each signal copy has an independent outage probability, then the outage probability for the entire time diversity transdermal link is equal to the outage probability for all M copies of provided data, and mathematically expressed by the equation shown here. On the other hand, transdermal optical system that incorporate wavelength diversity is a communication system with a composite transmitter that broadcasts a signal at many operational wavelengths at the same time to multiple receivers, each of which is tuned to pick up the signal at single wavelength. The explanation behind this is as follows. Assume that M transmitter at M distinct wavelength send the signal concurrently in transdermal optical wireless system consists of M trans receivers. So the statistical channel model for wavelength diversity scheme is shown in this equation. On the other hand, assume that each communication link will operate independently from other lines as long as the necessary distance between the receiver is maintained. The outage probability is reduced to the product of the probabilities of each individual outage, as shown in this equation. Now I will discuss the result obtained. Numerical results are represented using novel closed form expression derived previously for system metrics. In order to confirm the accuracy of a numerical result, the results of the Monte Carlo simulation are additionally provided. A good agreement was concluded between the numerical and simulate results. Okay. Here, numerical results for the achieved outage probability of time and wavelength diversity transdermal optical system, and their change for the several system factors that could impact the transdermal optical wireless system efficiency. It's assumed that M, the time diversity parameter, can take on the values 1, 2, 3, and 4 with single increment. Considering severe and moderate pointing error condition, which represented by the value of psi. So this figure shows the outage probability enhancement when going from m equals 1 to m equals 2, 3, and 4 for multiple signal to noise ratio threshold value under moderate pointing error. Furthermore, it's obvious that as the effect of the pointing error become more severe, which mean as the value of psi decreases, the outage probability gets worse for fixed threshold signal to noise ratio. The outage probability is expressed in terms of normalized signal to noise ratio for validation process. As we see, it's clear that the existence of a stronger time diversity scheme, regardless of the pointing error degree, a greater value of M result in significantly better availability results for the transdermal optical wireless link. Okay. In this figure, the outage probability is displayed as function of a skin thickness for a different value of M. As discussed previously, as skin thickness increase, link availability decrease. Moreover, an improvement in outage probability when moving from M equals 1 arrangement to M equals 2, 3, and 4. This figure demonstrates the outage probability for various values of M as a function of the operating wavelength. As we see, the smallest value of outage probability will occur at lambda equals 1,200, which represent the optimal transmission wavelength. The results emphasize that using multiple link will improve link availability. For the case of wavelength diversity scheme, results for outage probability for the same system parameters is presented in the figure. Here, the outage probability versus skin thickness is presented for a specific instantaneous signal to noise ratio threshold, which equals 1, and under moderate pointing error. Initially, significant outage probability decrements as skin thickness decrease was obtained. Either way, using wavelength diversity results in notable improvement in outage performance. The outage probability is then estimated as function of psi, which represents the pointing error level, where the figure displays the acquired result, and the using of wavelength diversity can greatly reduce the outage probability of a typical transdermal optical wireless link, particularly when more wavelengths are used. Additionally, lower signal to noise ratio threshold level and weaker pointing error can considerably reduce the transdermal optical wireless link outage probability and enhance system performance. Finally, the conclusions of this study, the outage probability for time and wavelength diversity models are evaluated against set of variable parameters, including skin thickness, pointing error severity, and wavelength. The result shows a significant dependency of the system link reliability on these parameters. Thus, such link parameter need to be carefully tuned prior to the transdermal optical wavelength design phase. Two, the results showed that zero pointing error is a significant factor in determining the quality and the effectiveness of transdermal communication test system. And finally, time and wavelength diversity techniques were deployed in the system to study their added value in the overall performance. A significant enhancement on the outage probability metric was noted. Thank you very much for your listening.